Good morning, students. I am Dr. P.S. Kaushik, Principal at Sri Digambar Institute of Technology, Dosa, Rajasthan. I am taking the 7th lecture on engineering mechanics. This subject belongs to 3rd semester of civil and mechanical engineering. Let us know what we learned in the last lecture. In the last lecture, we solved a problem based on parallelogram law of forces. Here we applied it was a simple problem. So, we applied the parallelogram law which shows that resultant of two coplanar concurrent forces will be represented by the diagonal formed by taking the magnitude of the two forces as the two consecutive arms of a parallelogram. The diagonal which passes through the point of concurrency, it represents the resultant. Say this is one force, this is another force. So, draw a parallelogram. This shows the resultant R. We proved it by just extend it the horizontal line and drop a vertical from it. This is say P and this is Q, making an angle theta. Then this angle will also be theta. This will be in magnitude equal to Q. Then this will be Q sin theta and this will be Q cos theta. This much will be P plus Q cos theta. If this is the angle alpha, then by applying Pythagoras theorem, we can say R equal to under root of P square plus Q square plus 2 PQ cos theta. Similarly, we can find out this angle alpha, which is equal to the height upon base, that is tan alpha will be equal to Q sin theta upon P plus Q cos theta. Then we studied the composition of forces and resolution of a force. Composition means finding out the resultant of a system of forces, and resolution means finding the components of a single force. Then we solved a more problem based on coplanar concurrent force system. Here take another problem. Here this is the force system, coplanar concurrent force system, constituting 20 Newton, 25 Newton, 30 Newton and 35 Newton, 4 forces making an angle from the eastern side, that is horizontal eastern side, that is 30 degree, 90 degree, 135 degree and 220 degree. These angles are calculated from the horizontal side counter clockwise. Like this. So, first resolve the forces horizontally. For example, this is your 20 degree 20 Newton force, its one component will be like this and other component will be this way. So, in magnitude we can calculate it here. So, this is your sine component, this is cos component. So, we can say 20 cos 30 is horizontal or 20 sine 30 is the vertical component. Similarly, for 25 Newton, its horizontal component is 0, then 30 degree Newton and then for 35 Newton. So, we can say 20 cos 30 plus 25 cos 90 plus 30 cos 135 plus 35 cos 220 Newtons, which comes out to be, because this angle is 0, so here is 0. So, this comes out to be minus 30.7 Newton. It means this horizontal component of the force will lie in this region somewhere. Now, resolving all forces vertically. So, summation V 20 sin 30, 25 sin 90, 30 sin 135, 35 sin 220. By calculation, it comes out to be 33.7 Newton. It means it will be above this line, here somewhere it will be in this region. We know that magnitude of the resultant forces are equal to under root of summation h square plus summation v square, which comes out to be 45.6 Newton. Now, direction of the resultant force, again tan theta will be found out summation v upon summation h, that is 1.098, and theta comes out to be tan inverse 1.098, which comes out to be 47.7. Since summation h, the horizontal component of all the forces, is negative and summation v is positive, therefore, the resultant will lie in the second quadrant. Thus, the actual angle of the resultant force will be 180 minus 47.7, that is 132.3 degree. Now, again take another example. A system of forces are acting at the corners of a rectangular block as shown in the figure. This problem is taken from Dr. Engineering Mechanics by R. S. Krugman. Again, resolve the forces. Horizontally and vertically, again summation h equal to horizontal component is the 30 Newton, it is towards left, then it is so and this one is towards right. So, summation is 25 minus 25 Newton. Then now resolving the forces vertically. Vertically, there are two forces, that is 50 Newton and 35 Newton. Both are direct downward. So, it is minus 85 Newton. The magnitude of the resultant force is given by this relation, which comes out to be 85.15 kilonewton. That is R equal to under root of summation s whole square plus summation v whole square, which comes out to under root of phi square plus minus 85 का whole square, which comes out to be 85.15. Direction of the resultant force is again using same formula. We know that tan theta is equal to summation v upon summation h, that is minus 85 upon 5, that is minus 17. Then theta is equal to tan inverse minus 17 the minus is missing, which comes out to be 86.6. So, theta is equal to 86.6. Since summation h is positive, summation v is negative, therefore, the resultant lies between 270 and 360 degrees. Thus, the actual angle of the resultant force will be 360 minus 86.6, that is 273.4 degrees. Now, next is coplanar non-concurrent force system. Till now we have studied only coplanar concurrent force system. As we have learned in the last lecture that the force system can be replaced by a single force called resultant. It was a bit easy to find the resultant on a coplanar concurrent force system, since the resultant will also act on the point of concurrency. But in case of coplanar non-concurrent force system, see the result. But in the case of coplanar non-concurrent force system, its point of application is also to be established. We will be using the principle of moment or lever rule to find the point of application, which states that if a number of coplanar forces are acting simultaneously on a particle, the algebraic sum of the moments of all the forces about any point is equal to the moment of their resultant force about the same point. We will be dealing with this concept of moment in the next lecture. Here we take a problem that a horizontal beam PQRS is 12 meter long, where PQ, QR and RS are 4 meter. Force of 1000 Newton, 1500 Newton, 1000 Newton, 500 Newton act on PQR and S respectively, as shown in the figure. The lines of action of these forces make an angle of 90 degree, 60 degree, 45 degree, 30 degree respectively with the polar axis of the beam. Find the magnitude, direction and position of the resultant force. Here, what do you mean by polar axis? Polar axis means, since a beam is normally, beam or column are normally having length much larger than their cross sectional dimensions. So, anything which is longer in length but cross sectional area are less, cross sectional dimensions are less, we call it a pole. You can take the concept of electric pole, pole vault. So, pole is the structural members which have its length, longitudinal dimension much larger than its cross sectional dimensions, and so we call it a pole. So, any axis along the pole or along the length or longitudinal axis in general term, we call it the polar axis. This concept we will be using frequently when we will dealing in the strength of material part. Here refer to the figure above. the magnitude of the resultant force, resolving all the forces horizontally, summation H equal to 1000 cos 90, 15 cos 1500 cos 60. Oh, 1000 cos 45, 500 cos 30, which comes out to be 1890 Newton. Now, resolving all the forces vertically using the same concept, it comes out to be 3256 Newton. Again applying the same formula, R equal to summation under root of summation H square plus summation V square, which comes out to be 3765 Newton. Direction of the resultant force, that let theta is the angle which the resultant force makes with the polar axis, that is PS, then tan theta is equal to summation V upon summation H, that is 3256 upon 1890 is equal to 1.72, then theta is equal to tan inverse 1.72 or theta is equal to 59.8 degree. Note, since both the values of summation H and summation V are positive, therefore, the resultant lies between 0 and 90 degree. Now, we have to find out the distance of the resultant from P. For that, let x be the distance between P and the line of action of the resultant force. This is the resultant force, this is the distance x, this much. Now, taking moment of the vertical components of the forces and resultant force about P and equating the same, which comes out, that is 3256 into x equal to 100 into 0 plus 1500 into 0.866 into 4, then 1000 into 0.07 into 8 plus 500 into 0.5 into 12, which comes out to 13852. And when dividing this by this, that is 13852 divided by 3256, then x comes out to be 4.25. So, this value is 4.25. Now, let us discuss some more on this topic. We will be dealing this moment in the next lectures, coming lectures. But what is a moment? Consider this is a point this is a lever which is acted upon by a force, say this force P, making an angle theta. Then this is its vertical component, this is horizontal component. Okay. The moment is the turning effect of a force is called moment. This is a force P acting, then this is a pivot point above, then this component is giving it a pull, that is P cos theta is giving it is a pull at the hinge, but this P sin theta is giving it a moment, that is counterclockwise rotation. Now, there are two ways to find out the moment, that is this is a d distance, then we can say m equal to P sin theta into d. But let us take it other way. This is your point about which this lever is will rotate, and this is your component, this is P. So, basically the distance it should be the shortest distance on the line of action. This is the line of action of this. We draw a vertical on this, then in that case this angle is theta, so this angle will be theta. It means this arm will be, this is d distance, then this arm will be d sin theta. Then in that case m will be p into d sin theta, which is same as was discussed earlier. So, we can say the force into shortest distance from the reference point. When we multiply these two, we find the moment of that force about this point. Now, next very important concept, that is free body diagram. This free body diagram, what it, for example, we have a structure, a body on which we are dealing with the force system, but we want to analyze any one part of that body, then we virtually remove that part from the body, virtually means imaginarily, and at the point of joint we give a reaction that is normal to the surface there, and thus the structure so removed from the main structure will be dealt with by external force, weight of that structure if considered, and the support reaction by arrow heads facing the point of disengagement at the point of disengagement normal to the surface. Internal forces if applicable. By considering the conditions of equilibrium, the force system is analyzed there. The following few examples will illustrate the free body diagram. For example, this is an aeroplane. Here the lift is facing upward, drag down backward, weight downward, and thrust forward. This is the free body diagram of an aircraft flying. Now take this sphere kept on the floor. Its weight is acting downward, but its reaction will from the floor will be acting upward. So, just we removed the floor from the sphere and we gave a force system like this. Here weight is acting downward, reaction is acting upward. This is the free body diagram for the sphere. Here note one thing, as I have told you earlier also, that this reaction is acting at the sphere, whereas weight is acting on the floor. So, it means these two forces are not cancelling each other, because these two forces are actually acting on different bodies. That is, weight is acting on the floor, whereas the reaction is acting on the sphere. So, they are not cancelling each other. Take another example. This sphere is kept in this if we remove these surfaces, then a force diagram is formed like this. This will be a free body diagram. When we remove this is the reaction we have shown at this surface vertical to the surface. This is reaction RB, this is reaction RA. And when we extend by using the principle of transmissibility, when we extend these forces beyond this, here we extended this force like this and weight is acting like this. Then that way this is RB, here RB, this is A, the RA, and such a diagram will be called as free body diagram. Sometimes we can see it a force diagram also. Another example, take this. This is the free body diagram for this beam. This is the beam whose free body diagram is to be drawn. What we have done? We have removed this beam from this hinge and from this hinge. Here we have shown this push for this, and for this hinge we have shown this is a push and this is a vertical. The force is 4 kilonewton acting here. So this constitutes a free body diagram for this beam here. A load diagram, we call it, this is a free body diagram. Again, this is the lever. This is the lever for which a free body diagram is to be drawn. Here we removed this lever from here and removed this from here also and from here also. We have removed this lever from this point and this point, and we have shown the reactions at this point, and this point, which are vertical to the surface. So this is the surface, इसके vertical, this is the force we have shown here, reaction. Again this is the surface, इसका vertical ये हो गया, तो हमने ये दिखा दिया यहाँ पर force, and this is the surface, इसके vertical ये हमने यहाँ पर दिखा दिया. So what it is, what are we have removed the supports and we have shown the support reaction at here and here and here. These are the support reactions. Reactions are always normal to the surface. So these are normal to this surface and this surface. So what is free body diagram? Again, free body diagram is used when we want to analyze the component of a structure. Then we remove that component virtually from the body, and from the hinge points or supports, we remove the supports and we give their reactions there which are vertical to the supports. Again you should know that this was a surface and this was a support. We removed it and we have given a vertical to this a reaction here. Similarly, this was support, we have given it like this. This was a support, we have given it like this. Direction, if these are not right directions of the forces, when we analyze, we will find a negative result. Then we can change the direction, that's way. So what it is showing, because we have considered the weight of the lever negligible, no internal stresses are being calculated because we have considered the body rigid. Hence, what we have here, we have the reactions at supports and the external force. So, as I told you earlier, a fluid wave diagram is a diagram for a member of a structure. We want to analyze the forces on that member. Then what we do, we virtually remove that member from the structure, and we denote the external forces acting, weight is considered of that member, and the support reactions, and if internal stresses are they to be considered, then they are also being shown. But in the engineering mechanics, for rigid body, what we want to show? We want to show the support reactions, weight of the member, and the external forces. Here in this expression, the weight of the member is also being neglected. Thanks for watching this video. Mail me on this mail for any query or suggestion. Thanks a lot.